Welcome. In today's class we are going to discuss the solar system. Before embarking on this discussion of the solar system, let us briefly recapitulate what we have done in the last class. This picture, by the way, shows you the different major constituents of the solar system, but before embarking on that, in the last class we discussed about the orbits of objects around the sun, and these are governed by Kepler's laws. Kepler had proposed 3 laws which were later on found to be a consequence of Newton's laws of gravity and the laws of motion. So, the first law which governs these orbits is that they move in ellipses with the sun at one of the foci, and these ellipses are governed by the equation. So, the equation of an ellipse, let me remind you, is this, where there are 2 parameters, the semi major axis and the eccentricity. Second law says that the radius vector from the sun to the planet sweeps out equal area in equal time, and the third law says that the period of the orbit is the square of the period is proportional to the semi major axis cube. So, it would be useful to keep these in mind as we discuss the solar system. The most dominant component of the solar system is the sun, and the luminosity of the sun is 3.9 into 10 to the power 26 watts. This is a very important quantity, and the solar luminosity is going to plays a very important role in the discussion, all of the discussion of astrophysics and astronomy, etc. It is denoted by L sun. So, this refers to the sun, a circle with a dot. This is the solar luminosity, and we shall refer to the luminosity of other astronomical objects in terms of this. This is the solar luminosity, and the value is given over here. So, it is the amount of energy that comes out of the sun in 1 second. Compare it to a typical 100-watt bulb, right. So, this is much more, just imagine 100 watt is 10 to the power 2 and this is 10 to the power 26 watts. Okay. The mass of the sun again is an important number, because other mass of other astronomical objects shall be discussed in terms of this. It shall be denoted by m sun, the mass of the sun, and this has a value 1.99 into 10 to the power 30 kilos, 30 kg. The radius of the sun is 6.96 into 10 to the power 8 meters. So, light takes approximately 2 seconds to travel from the center of the sun to the periphery if it were to travel in a straight line. That gives you an idea of the radius, of the size of the sun. The size of the earth, remember, is around 6,000. The radius of the earth is around 6,000 kilometers, the size of the earth. So, this gives you an idea of how many times larger the sun is in physical in the length, and the temperature of the sun is 5800 Kelvin roughly. The other important thing as far as the solar system is concerned is the distance from the earth to the sun, and this distance is 1.50 into 10 to the power 11 meters. This distance is an important number. It is referred to as the astronomical unit. So, 1 astronomical unit is 1.5 into 10 to the power 11 meters, and we shall refer to distances in the solar system and in the neighborhood of the solar system in this unit of which is the astronomical unit, AU. Okay, so it is an important number to keep in mind. So, with this background about the sun, some figures about the sun, this is a picture of the sun. So, the solar system consists of sun and the planets, and the sun, as I told you, is the most dominant object in the solar system. It contains 99.85% of the known mass of the solar system. So, nearly all the mass in the solar system is in the sun. You can think of as if someone were to look at the solar system from outside, they would mainly notice the sun. The planets would not figure in the picture at all, because it is less than 1% of the total mass. It is some kind of debris floating around in the around the sun, you can think of it that way. Okay, after the sun, the planets contain 1.135%, and there are other objects like comets, the Kuiper belt objects, planetary satellites, minor planets, meteoroids, etc., interplanetary medium. They contribute 0.015%. Contrary to the distribution of mass, the planets contain the majority of the angular momentum. The sun is concentrated at the center. So, if you look at the total angular momentum of the solar system, which we know is conserved, that is mainly in the planets and not in the sun. The sun rotates around its own axis, but that does not contribute much, it is mainly in the planets. So, there are 8 planets in the solar system, and this is the same picture again of the sun. This is the sun, and these are the 8 planets shown over here. The planets, the size of the planets are to scale. So, the size, this is what, so if you draw everything to scale, this is what the entire thing looks like. The sun is really enormous, the other planets are minuscular, these planets here are minuscular, and the outer planets are relatively larger. Okay. And these planets are starting from, the distances are not to scale, the distances between the planets are not to scale in this picture, only the size of the planets are to scale. Starting from inside, you have Mercury, Venus, and then you have Earth, then Mars, Jupiter, Saturn, and Uranus. You may be wondering what happened to Pluto. Well, a new word has been coined, which is Pluto. Basically, Pluto has been thrown out. I mean, it is not considered to be a planet anymore. Okay. So, it has been, you may say, ejected from this exclusive class of objects called planets in the solar system. We shall come back to what Pluto is considered to be later on in this class. And we have already learned that all the planets move around the sun in an ellipse with the sun as the focus. So, we have already learned this. Now, these orbits are all nearly coplanar. Mercury has the, okay, and they are nearly circular. So, two things. So, they are nearly circular and they are nearly coplanar. So, the eccentricity is quite small. Mercury has the largest eccentricity. Similarly, Mercury has the largest inclination, the orbit of Mercury, it is 7 degrees. And all the planets barring Mercury and Venus are known to have planetary satellites. So, the moon, what we call our moon, is an example of a planetary satellite. So, barring Mercury and Venus, all the other planets are known to have satellites. Let me just go through some data which we shall come back to as and when required. So, this shows you the semi-major axis of the planets. We have already discussed what the semi-major axis is. It decides the size of the ellipse. and they are all tabulated here. So, you can see that it increases, and Mercury is 0.3 times the distance, 0.3 roughly 0.3 0.4 astronomical units, whereas Neptune, the furthest planet, is 30 astronomical units. Okay. The eccentricity, you can see that Mercury has an eccentricity of 0.2. All the other planets have orbits with eccentricities less than 0.1. It starts from the second decimal place. Similarly, this shows the inclination. They are very close, they are all more or less in the same plane, the orbits are in the same plane. Mercury has the largest inclination. These are okay. The physical parameters of these planets, those were the orbital parameters. The physical parameters are shown here. So, this shows you the radius, and you can see that all the way to Mars the planets have radius of the order of few thousands of kilometers. Once you reach Jupiter, it is of the order of 70,000 kilometers. There is a substantial jump, and these are all of the order of tens of thousands of kilometers, Jupiter and beyond. The mass also, you can see up to Mars the mass is quite low, they are of the same order, the masses are of the order of 10 to the power 24 kilos, that is the first point. So, these are in units of 10 to the power 24 kilos, these were in units of kilometers. So, this is in units of 10 to the power 24 kilos, and Earth has a mass of 5.97 into 10 to the power 24 kilometers. Earth and Venus have comparable masses, Mercury and Mars have smaller masses. Jupiter has a mass which is 300 times larger than that of Earth, and Jupiter itself contains more material. I think it is twice as much more material mass as the rest of the planets in the solar system. So, it is really enormous. Okay. And this shows you the rotation rate and the orbital period. The orbital period you know is related to the semi major axis. So, it will keep on increasing as you go further and further out, and this shows you the rotation period of the planet, sidereal rotation period in days. Okay. So, we shall come back to these numbers as and when required as we go along today's class. So, the planets have the planets in the solar system are roughly divided into two groups of planets. The inner planets have different properties from the outer planets. So, the inner planets are the ones shown over here, and this picture shows you the position of the inner planets on 10th January 2010, and you can visit this website over here, which is the Solar System Live, and if you visit it today or tomorrow, it will, whenever you visit it, it will show you the position of the planets at that instant of time. Okay. And the whole all the planets in the solar system, if you view it from the north pole, if you look down from the north pole of the earth, so you go above the north pole of the earth, the celestial north pole, you may say, from there you look down at the solar system, all the planets rotate in a counterclockwise direction. They all have the same direction of angular momentum, and the orbits are nearly coplanar. So, the direction angular momentum of all these orbits are nearly aligned, Okay. The inner planets, Mercury, Venus, Earth and Mars, they are referred to as the terrestrial planets, because they are composed of rocky material like the Earth. It has a solid, it is a solid planet. Not all planets are solid. Okay. The Earth we know has a solid surface on top of which there is an atmosphere. So, all the 4 inner planets have this kind of a structure, they have a solid rocky constitution like the Earth, okay, which is why they are called terrestrial planets. They have relatively high densities and slow rotation. So, this shows you the rotation, and this is the rotation period. So, Mercury has an extremely slow rotation long rotation period. It is Mercury and Venus both have pretty long rotation periods. This is 58 days and this is 243 days. This is the rotation period of the Earth Moon binary, and this is the rotation period of Mars, which is comparable to the rotation period of Earth. Yes, right. The minus sign shows you the direction of the rotation relative to the direction of the orbit. Okay. So, we shall come back to this a little later. For Earth, we know that the rotation and the orbit are in the same direction, which is why there is a positive sign. So, for all the planets where the rotation and orbital motion are in the same direction, there is a positive sign. So, these have relatively slow rotation, and they have solid surfaces, which I have already mentioned, and these planets do not have rings or many satellites. There are two which have satellites, Earth and Mars, but they do not have a large number of satellites, and none of them have rings. Okay, and they have relatively low masses. So, this shows you the masses, and Earth we have seen is 6 into 10 to the it has 6 into 10 to the power 24 kilos. Venus is comparable mass, it has got around 5 into 10 to the power 24 kilos. Mercury has a much smaller mass, it is 0.3 into 10 to the power 24 kilos, and Mars also has a smaller mass, it is 0.4 into 10 to the power 24 kilos. So, you may say that roughly there are two planets which have comparable mass, Earth and Venus, and Mercury and Mars have got much smaller masses, 10 times smaller. Mercury is the planet with the smallest mass. So, these are the inner planets. Now, let us discuss the outer planets, of which there again are 4. So, again this picture shows you the position of the outer planets on the same date as that of the inner planets, and outer planets also all rotate in the counterclockwise direction when viewed from the north pole of the Earth, above the north pole of the Earth. Okay. And there are 4 outer planets. These 4 planets are Jupiter, Saturn, and then we have Uranus and Neptune, these 4 planets. The trajectory of Pluto is also shown here, but as I have told you, Pluto is no longer considered to be a planet for reasons which we shall discuss as we go along in today's lecture. Now, these outer planets are much larger, these are referred to as giant planets. The 4 outer planets are referred to as giant planets. Let us see why they are referred to as giant planets. So, the masses, let us look at the masses. The mass of Jupiter, as I have told you, is roughly 300 times, more than 300 times the mass of Earth, and the mass of Saturn, which is next, is around half of or maybe less than half, 1/3 of that of Saturn, and then you have Uranus and Neptune, but these all of them are at least 10 times, more than 10 times larger in mass than that of the Earth. So, these are much more massive, that is the first thing, which is one thing. And if you look at the radius in kilometers, Earth has a radius of 6,371 kilometers, which is the largest amongst all the inner planets, whereas the radius of Jupiter is 69,911. So, it is roughly 10 times larger in radius. Okay. So, these are much larger. You can similarly see that Saturn, Uranus and Neptune also have radius which are tens of thousands of kilometers. So, these planets are really giants compared to the 4 inner planets, and they have low densities relatively. They all rotate quite rapidly. So, if you look at their sidereal rotation periods, they are all less than a day, as you can see over here. So, these are these enormous objects which are rotating faster than the earth. So, you can imagine they are quite different, and they all have strong magnetic fields. Earth we know has a magnetic field. Mars possibly, it is believed, had a magnetic field. So, Earth's magnetic field is generated from within the earth. Mars also possibly had at some time had a magnetic field. Mercury also possibly has a magnetic field. Okay. But these magnetic fields are much weaker compared to those of these giant planets, which have got much stronger magnetic fields. Now, the giant planets, if you look at them, Jupiter and Saturn again are different from Neptune and Uranus and Neptune. Okay. So, Jupiter is the largest and Saturn is the second largest planet. So, these are the largest and second largest planets. Now, these planets are mainly made up of hydrogen and helium. They are largely gaseous, and they have very deep atmospheres. So, both these planets are largely gaseous, hydrogen and helium, and the atmosphere is very deep, and it is not clear. It is believed that there is a solid core inside, but there is no, as far as I know, that there is no direct observational evidence for the fact that they have a solid core inside. So, they are largely gaseous, big gaseous objects, and they are also referred to as the gas giants. Neptune and Uranus, these are the third and fourth largest planets. They are mainly made up of ice. So, this is frozen water, and in addition to water, I have missed out, sorry, it has come here by mistake. In addition to water, you also have ammonia and methane. So, these are mainly made up of frozen water, ammonia and methane. These are astrophysical ices, and it is not solid, it is a fluid. So, it is like a fluid slush of, you may think of frozen of ice made up of water and ammonia and methane. In addition to that, there are also rocks, very small condensates, which are made up of silica and metal. So, these are metal and silica condensates inside, and it has a thin atmosphere of hydrogen and helium also, small, relatively small atmosphere of hydrogen and helium also. These two planets, Neptune, Uranus and Neptune, are referred to as the ice giants. Okay. So, we have in brief, I have told you about the 8 planets that make up the solar system, and I have also told you about some properties of these planets. Now, let us consider the rotation of these planets, which was the question that was asked. So, this picture, these pictures over here show you how these planets rotate relative to the direction of their orbital motion around the sun. Okay. And most of the planets are doing prograde motion. Okay, so most of the planets have direct rotation or prograde motion. Venus and Uranus are the only exceptions, and they are undergoing retrograde motion. So, if you look at this picture, this is Mercury and this is Venus. Venus is inclined opposite to the direction in which it is orbiting the Sun. This is Jupiter. These are more or less aligned with the direction of orbital motion, but this is aligned in the opposite direction. These planets are all roughly inclined in nearly the same direction, and you have Earth, then you have Mars, Saturn, and you have Neptune, and Uranus has its rotation axis orthogonal to the direction of the orbital motion, and so does Pluto, but Pluto is no longer considered to be a planet. So, the bottom line of this entire discussion is that most planets are doing prograde or direct rotation. The orbital motion and the rotation are roughly aligned. Two exceptions are Uranus, which is orthogonal, and Venus, which is opposite, directed in the opposite way. Okay. So, given these facts and this idea of the solar system, it is very interesting to ask, how did the solar system originate, where did it come from? So, it is now believed that the solar system, what is the basis of this, what are the information, okay, on which this whole thing, what are the information that are useful if you want to make some idea about the origin of the solar system. The basic fact is that the orbits of all the planets are nearly coplanar with the ecliptic plane. Ecliptic is the plane in which the Earth moves around the Sun, and all the other planets are nearly coplanar. That is, we have seen this. Mercury is the one which is the most inclined, and the rotation axis of nearly all the planets are also inclined, and the Sun are all normal to the ecliptic, nearly. Okay. There are two which are exception, that is Venus is opposite and Uranus is orthogonal, but other than that all the other planets also have their rotation axis. The Sun also has its rotation axis orthogonal to the ecliptic plane. So, not only are they revolving around the Sun with the same angular momentum, they are also rotating around the Sun, and the Sun itself is rotating with an angular momentum in the same direction. So, this alignment of the angular momentum suggests that the solar system formed by the fragmentation of a spinning disk of gas. That is the main thing. So, the fact that the angular momentum of nearly all the objects in the solar system are aligned seems to suggest that the entire thing formed by the fragmentation of a spinning disk of gas. Okay. And the entire process is believed to have occurred 4.5 billion years ago. That is the estimated age of the solar system. This age has been estimated from study of radioactive isotopes, abundance ratio of radioactive isotopes in the solar system, meteorites, etc. So, this is the nebular hypothesis of the solar system. So, initially you had a cloud, a nebula refers to a cloud, you had a cloud of gas in the and dust in the Milky Way, and then at some time this starts to collapse. That is what is shown over here, and this collapse of the of this nebula, of this cloud of gas and dust, could possibly have been started off by a supernova explosion in the vicinity. So, supernova could have gone off in the vicinity, and the blast from that could have had an impact on this cloud and caused it to start to collapse. And the cloud which we are considering has some initial angular momentum, and as it collapses the angular momentum has to be conserved, as a consequence it starts spinning. So, you have the object getting smaller, since the angular momentum has to be conserved. Angular momentum we know is omega square r. If this is the direction of angular momentum, this is the angular velocity omega, then the angular momentum is omega into r squared, velocity into distance, and if you make r small, then the omega has to go up because the angular momentum is conserved. So, as this object, as this gas cloud, as this nebula collapses, it starts spinning faster and faster. So, just visualize this. There is this cloud which has been drawn spherical for just for visualization, and it is collapsing. So, it is spinning quite rapidly now after it has collapsed, and it cannot collapse any further because it would require a tremendous amount of spinning, but there is nothing to prevent it from collapsing in the direction. So, if this is my cloud, it is, if it were to try to collapse further in this direction, it would have to spin tremendously faster. Okay. So, that is what prevents it from collapsing in this direction, the centrifugal force, but there is nothing that prevents it from collapsing in the direction of along the angular momentum axis, because if it collapses this way, that does not have any influence on the angular momentum. So, this cloud which is spinning then collapses in the direction of the angular momentum. So, if the angular momentum is oriented this way, if it is spinning this way, it will collapse along this direction, and as a consequence of this collapse, it will possibly form something that looks like this, a disk around a maybe overdense central overdensity. Okay. So, you have a spinning disk at the end of the day, and this spinning disk then fragments, and the bigger fragment in the center forms the sun, and the fragments in the periphery form the planets. Okay. So, each thing over here fragments, and it forms a planet, and since the entire thing has the same angular momentum, the spins of each of these individual things. So, as this collapses, so this is showing you the collapse of one of these small fragments. As this collapses, it will again spin faster, and but the spins of all of these things will be aligned because the angular momentum of the initial thing is aligned. Okay. So, this is what is believed to have possibly happened, which gives rise to the protoplanets and planets, and then later on these form proto sun and planets, and later on these collapse for further, and you have star formation, the sun being ignited, nuclear fusion taking place at the center, and these planets being formed with the peripheral fragments. Okay. So, this is the currently accepted picture for the formation of the solar system. So, having briefly discussed the a scenario of a possibly viable scenario for the formation of the solar system, let us now go back and take a look at the solar system again. So, this is a picture of the inner solar system again. Remember, I had shown you a picture right at the start. This is the inner solar system. This is a picture of the same region of the solar system, but notice that this picture shows you, in addition to the planets, it also shows you some more objects, and these objects are densely inhabit a region over here, and there are some distributed here and here also, which we shall come to these later. But the point here is that in addition to the planets, you also have other kinds of objects in the solar system, and the yellow dots over here show you what are called asteroids. yellow. So, the yellow dots are asteroids. This shows you the side picture of the same thing of the inner solar system. So, you have asteroids. In addition to asteroids, you also have comets. So, the white ones, the white dots show you the position of the comets on 1st January 2010. The positions obviously will change with time. So, they will be somewhat different today, quite different possibly today. But this gives you an idea that in addition to the planets, you also have other kinds of objects, and these are possibly fragments. So, when this fragmentation occurred, the fragments in this region coalesced to form a large object, a protoplanet, and then a planet, but there could be fragments which did not coalesce and which are hanging around, and these possibly we see as asteroids. And so, you have these asteroids over here, the yellow ones, and you have the comets, the white objects. Okay. And the outer orbit here is the orbit of Jupiter. Okay. This is another picture now of again of the outer, this time of the outer solar system. The outer solar system, remember, just let me just a thing which I should point out, I had not made this point before. The inner solar system extends only to 1.5 astronomical units. So, when I show you a picture of the inner solar system of the inner planets, it extends only up to the orbit of Mars extends up to 1.5 astronomical units. It is a small part near the center. Once we include the other planets like Jupiter, Saturn, Uranus and Neptune. So, Jupiter is at 5 astronomical units, this is at 10, this is at 20 and this is at 30. Once we introduce these 4 planets 5, 10, 20 and 30 astronomical units roughly, the orbits of the inner planets become a very small thing at the center. So, you really cannot, it is difficult to show all the orbits together. Okay. So, that is a point to remember, that the scale over here, the outermost Mars is 1.5 astronomical units, whereas this is 30 astronomical units. Okay. So, when you are looking at this picture, this shows you Jupiter, which is 5 astronomical units, and everything here is so this is Mars, which is 1.5 astronomical units. This picture goes out to this is Neptune, and this is at 30 astronomical units. These inner planets are all a small thing over here. Okay, here again you see that in addition to the planets, you also have these asteroids and comets. The trajectory of 2 very prominent comets, the Halley comet, this is the Halley comet, comet Halley, which is very famous, and this is the comet Hale-Bopp, this orbit over here, are also shown. So, here again you can see this is the comet Hale-Bopp. Comet Hale-Bopp does extends, can you, I hope you can see the picture of comet Hale-Bopp's orbit. It extends beyond, much beyond this picture. Okay. And these all of these objects over here, so these comet Halley and Hale-Bopp, their motion also follows Kepler's laws, because they are also orbiting around the sun, doing a gravitationally bound orbit around the sun. So, you can imagine that the period of this would be extremely large.
So, the orbits are not clear in the picture.
Okay, yeah, I think we shall, they are possibly clearer in this picture. Yes.
The orbit of the comet Halo also,
Yeah.
should be coplanar or isn't it coplanar?
No, these orbits, the comets, as comets do not have coplanar orbits. There is no reason why that should be coplanar, right. So, they are not coplanar. Okay. This shows you the distant solar system. The scale of the picture has now increased substantially. So, 30 astronomical units is somewhere over here. So, the scale here extends beyond 50 astronomical units, and you can see the orbits of these comets. In addition to these comets and meteoroids, asteroids, you also have these objects Eris, Sedna, etc., which have been shown over here. So, these objects over here are not planets whose orbits have been shown over here. These are objects which we shall take up for discussion subsequently, and they are objects which are located in the distant solar system, and these objects also orbit around the sun. So, to give you two names, one of them is called Eris and the other one is called Sedna. Okay. They also are in orbit around the sun. Now, I would like to draw your attention here to the orbit of Pluto. This is the orbit of Pluto. It cuts the orbit of Neptune over here, and then it goes out again and it passes like this. And the point I would like to make is that the orbit of Pluto passes through this very dense kind of region filled with asteroids. So, region quite densely filled with asteroids. The orbit of Pluto passes through this region which is filled with asteroids. You can see it here. This is these asteroids all roughly are, the orbit of Pluto passes through these region filled with asteroids. Okay. And another point is that these orbits, these masses which are these objects which are here, Eris, Sedna, etc., they have been discovered only recently, and they are found to have masses comparable to the mass of Pluto. I have not shown the mass of Pluto anywhere, but these objects are comparable. Okay, this shows you the same picture, a bigger view of the same picture. So, here you can see clearly that this is the orbit of Pluto. The other planets interior to Pluto roughly have more or less circular orbits. Pluto has this is the orbit of Pluto. It has a very kind of eccentric orbit, and it cuts the orbit of Neptune at 2 points. So, sometimes it is closer than Neptune, sometimes it is further than Neptune. This and it passes through this through these to the position of these meteorites, asteroids, sorry, of these asteroids, through this asteroid belt. Okay. In addition, this is Sedna. This is the orbit of an object, astronomical object called Sedna, which also has this enormous orbit around the sun. This is Eris, another object called Eris, which has this orbit around the sun, and this is another object which is orbiting the sun. This is the orbit of Hale-Bopp, which goes out. With this picture in view, let me briefly discuss the question, why is Pluto no longer considered to be a planet? When we were in school, and I presume when you were in school also, you might have learned that there were 9 planets, and Pluto was taught to be one of the planets, but it no longer is considered to be a planet. Okay. So, the main thing is that observations, one of the main things was that observations showed that there exists a large number of objects beyond Neptune, and many of these objects could possibly have masses comparable to Pluto, even not larger. So, then it was a question of do we include all of these objects as planets in the solar system, or do we, how do we classify these? Okay. So, finally in the year 2006, the International Astronomical Union at its general body meeting passed a resolution, and in this resolution in 2006 they defined the conditions that an object has to satisfy, celestial body has to satisfy if it is to be a planet. And these conditions are that a planet is an object, is a celestial body A that is in orbit about the sun, and B it possesses sufficient self gravity to overcome rigid body forces, so that it assumes a hydrostatic equilibrium nearly round shape. Okay. So, the earth, for example, the gravitational attraction of the earth is sufficient to overcome various other forces, rigid body forces between the material that makes up the earth, the solid substance that makes up the earth. It is finally assumed a hydrostatic spherical shape. Okay. It could have been an irregular shaped rock, for example, but gravity is sufficiently strong, has been sufficiently strong to make it into a kind of bound spherical object. That is the second condition. The third condition is that the celestial body has cleared the neighborhood around its orbit. So, the orbit of the astronomical object should not be littered with all kinds of asteroids, etc. It should have enough gravitational attraction to have pulled in all the asteroids, etc. that are in its orbit, in the neighborhood of its orbit. And as it goes around, so the earth goes around the sun once a year, so it would have by now, if it is a planet, it would have had enough gravitational force attraction to have pulled in all the smaller objects in the neighborhood of its orbit over the period of time. So, over a period of few billion years it would have gone around many times, and it would have by now attracted to it and all the smaller objects in its neighborhood. Okay. So, if you look at the orbit of the earth, for example, or of the other inner planets. So, these are the orbits of the inner planets, and you see that they are relatively clean. The asteroids start from beyond the orbit of Mars. So, there is this region from 1.5 astronomical units. So, the Mars is at 1.5 astronomical units and Jupiter is at 5 astronomical units. So, there is this enormous region over here 1.5 to 5, so 3.5 astronomical units in distance, which is where the asteroids reside, and the region in between inside here is relatively free of asteroids. So, these planets, these celestial bodies have cleared their orbits of any kind of debris. Similarly, the outer planets shown over here have also all cleared their so these are the outer planets shown over here, and they have all cleared their orbits of things hanging around, debris. Whereas Pluto, you can see its orbit passes through this region which is densely filled with asteroids, other objects. So, Pluto does not satisfy this criteria. Now, to accommodate objects like Pluto, the International Astronomical Union introduced something called a dwarf planet. So, Pluto is now a dwarf planet. So, what is a dwarf planet? A dwarf planet is a celestial body that A is in orbit about the sun, B it has sufficient mass for self gravity to overcome the rigid body forces and to assume roughly to be in hydrostatic equilibrium and assume a roughly spherical shape. So, the gravitational self gravity of Pluto is adequate for it to assume a roughly spherical shape. The other forces are the electrostatic repulsion, electromagnetic forces, which say prevent this, hold the pen. The pen is not in is not a self gravitating object, it is held together by the electromagnetic forces and it maintains a distinct shape of its own. But if it were a self gravitating object, then the gravitational force of the different parts would be adequate to overcome these forces and make it into a spherical object. Okay, so Pluto is adequately massive for that, but Pluto has not cleared the neighborhood around its orbit. So a dwarf planet is an object, celestial object, that has not cleared the neighborhood around its orbit. Further, a dwarf planet should not be a satellite of another planet. So there are satellites, so the moon for example is also orbiting the sun. It is roughly spherical, it has enough self gravity possibly. Okay, all other objects except satellites. So this is a dwarf planet and Pluto is a dwarf planet. Now there is a third class of object which was also defined, and all other objects except satellites orbiting the sun shall be referred to collectively as small solar system bodies. So there are three kinds of things orbiting the independently orbiting the sun. One are the planets, the other second is the dwarf planets, and anything else which is not a satellite shall be classified as a small solar system body. Okay, so these are the three kinds of things in the solar system besides satellites which are orbiting around planets. Okay. So as I have told you, Pluto is now a dwarf planet according to the above mentioned definition, and it is recognized as a prototype of a new category of trans Neptunian objects. So there are a large number of objects which have been found now beyond Neptune, which are possibly will be, many of them will possibly be classified as dwarf planets, and Pluto is taken to be a prototype of such an object. And there are now at the time when when I prepared this some time ago, there were several designated dwarf planets. So this is a list, you have one Ceres and then you have this Pluto and you have Eris over here, and possibly by now there are several more dwarf planets which have been discovered. So before we end for today, let me briefly recapitulate what we have done. Today we have discussed the solar system, which has the most dominant component of which is the sun, and the earth sun distance I have told you is the astronomical unit. The mass of the sun is also a very important number, the luminosity of the sun too is an important number. The planets in the solar system, 8 of them, are roughly divided into two. You have the 4 inner planets and the 4 outer planets. The inner planets are relatively small, they are solid, referred to as terrestrial planets, they all rotate slowly, and the furthest one is Mars, which is at 1.5 astronomical units. The 4 outer planets, starting with Jupiter, Saturn, Uranus, Neptune, they have a point which I forgot to make, all of them have several satellites and some of them also have rings. That is the point I forgot to make. So Saturn we know has rings, there are other planets also which have rings. So the these planets are several times larger than the inner planets. The Jupiter, the most massive planet, is 300 times larger in mass, 10 times possibly larger in radius, and it extends, the outer planets extend all the way up to 30 astronomical units. Then I showed you that there are objects beyond Neptune which are referred to as trans Neptunian objects, and we have asteroids and comets also. Then we discussed the definition of a planet, and we saw that Pluto is no longer considered to be a planet because it does not satisfy this definition. It has not cleared its orbit of other objects. There are large number of other objects orbit of Pluto, in Pluto's orbit, and there are now many other such objects of similar mass as Pluto, all of which are classified as dwarf planets. So, this is a rough overview of the solar system. Let me stop here for today. In the next class, we shall continue our discussion of the solar system.